Have you ever wished for more time in a day? Perhaps you felt the relentless march of seconds, wishing you could just pause the world for a moment. We all have those days where 24 hours simply doesn't seem like enough to accomplish everything we need to do. Well, tomorrow, July 22nd, 2025, mark your calendars, because this day might just be a little different. It could be the shortest day in recorded history, a fleeting moment, almost imperceptible, but significant nonetheless. Scientists say the Earth will complete one full spin, that familiar rotation that gives us day and night, just a bit faster than usual, a subtle acceleration in the grand cosmic dance. Don't worry, you won't notice. Your morning coffee will still taste the same, and your commute will be just as long. The change is just a few milliseconds, a fraction of a second, far too small to affect your daily routine. You won't suddenly find yourself with extra time on your hands. But for scientists, it's a big deal. These tiny variations are like whispers from the Earth itself. It signals something interesting is happening with our planet. A shift in the delicate balance of forces that govern our world. We think of a day as exactly 24 hours, a constant, reliable measure of time. But Earth's spin isn't perfectly steady. It's more like a spinning top, subject to subtle wobbles and variations. It can speed up or slow down by tiny amounts. These fluctuations are influenced by a complex interplay of factors. Tomorrow's expected speed up is another record in a recent trend, a sign that something significant is underway. Earth's days have been getting shorter, a subtle but persistent change in the length of our days. For a long time, Earth was actually slowing down, gradually increasing the length of each day. But now it's speeding up, reversing the trend and presenting a new puzzle for scientists to unravel, breaking records over the past few years. Each new record is a data point, a clue in a larger investigation. Why is this happening? What forces are at play that are causing our planet to spin faster? That's the mystery scientists are eager to solve. They're using sophisticated tools and techniques to understand the underlying causes. These tiny changes are invisible to us, imperceptible in our daily lives, but they're a huge clue about the powerful forces shaping our world. Forces that operate on a planetary scale. Your alarm will still ring on time and life will proceed as normal. And the sun will set as usual. The rhythm of our days will remain largely unchanged. The real story is about the science, the quest to understand our planet, how our planet's rhythm is shifting, a subtle but significant alteration in the Earth's rotation. Each new record is a piece of a fascinating puzzle, a piece that helps us understand the complex workings of our planet. What's causing this sudden hurry? What's making the Earth spin faster than it has in recent history? That's what makes science so exciting. The thrill of discovery, the pursuit of knowledge, and the constant quest to understand the world around us. Stay tuned as we explore the forces behind Earth's changing spin. We'll delve into the science and uncover the mysteries behind this planetary phenomenon. For centuries, humans measured the length of a day by observing the sun's journey across the sky. Sunrise marked the beginning, and sunset signaled the end. But measuring a day isn't as simple as watching the sun rise and set anymore. Our understanding of time and the tools we use to measure it have evolved dramatically. Today, scientists use a network of sophisticated radio telescopes strategically positioned around the world. These aren't your backyard telescopes. They are massive, complex instruments capable of detecting faint signals from the depths of space. These telescopes are pointed towards incredibly distant objects like quasars, supermassive black holes at the centers of galaxies, emitting powerful radio waves. These quasars act as fixed points of reference in the vast expanse of the cosmos. This method, called Very Long Baseline Interferometry, or VLBI for short, is a technique that combines data from multiple radio telescopes to create a virtual telescope the size of the Earth. This allows them to measure Earth's rotation with incredible accuracy, far beyond what would be possible with a single telescope. It's like having a giant eye on the sky, capable of detecting the slightest wobble or change in our planet's spin. As Earth spins on its axis, each telescope in the network sees the quasar at a slightly different time. This difference, though minuscule, is crucial for precise measurements. By meticulously comparing these signals, scientists can determine the exact time it takes for Earth to complete one rotation. Sophisticated algorithms and powerful computers analyze the data, allowing scientists to detect even the tiniest changes in our planet's spin, variations imperceptible to our everyday senses. The data obtained from VLBI is then used to define universal time, or UT1, which is the official timescale based on Earth's actual rotation. It's the most accurate representation of the Earth's spin. This is different from Coordinated Universal Time, or UTC, which is the time standard used for most practical purposes. UTC is kept incredibly steady by atomic clocks, which are far more stable than the Earth's rotation. When we say a day is shorter, it means UT1, the Earth's actual rotation, is a bit ahead of UTC, the atomic clock time. The Earth is spinning slightly faster than usual. These tiny differences, measured in milliseconds, reveal when Earth is spinning faster or slower, providing valuable insights into the forces affecting our planet's rotation. It's amazing that by listening to faint signals from the edge of the universe, signals that have traveled billions of light years to reach us, we can track our planet's every move with such precision, revealing the subtle variations in its rotation. This cosmic dance, this intricate interplay of celestial objects, connects us to the farthest reaches of space, allowing us to understand our place in the universe. Our tools, these incredible radio telescopes and sophisticated algorithms, let us watch every step of this dance, every subtle shift in Earth's rotation. The precision is mind-blowing, a testament to human ingenuity and our relentless pursuit of knowledge. We're talking about measuring time down to fractions of a millisecond, a level of accuracy that was once unimaginable. That's how we know when Earth sets a new record, spinning just a tiny bit faster or slower than it ever has before. What's a millisecond anyway? It's a unit of time we often hear about, especially in the context of technology and science. But what does it really mean? It's 1,000th of a second, an incredibly brief duration, so fast that our brains can't even consciously register it as a distinct moment. Think of it as a fleeting instant, a mere blip in the grand scheme of time. A blink, something we do without even thinking, takes about 300 milliseconds. That gives you a sense of scale. The changes in Earth's rotation, imperceptible to us in our daily lives, are even smaller when measured on this scale. Computers and high-speed machines, however, operate routinely in the world of milliseconds. Their processors execute millions of instructions in that tiny fraction of a second. To put it in perspective, a hummingbird flaps its wings with incredible speed, completing a full flap in about 20 milliseconds. When we talk about the Earth's rotation, the variations we're interested in are tinier still, almost unfathomable. When a day is shorter or longer, it's by just 1 or 2 milliseconds. These are minuscule changes, but they add up over time. We can't feel these shifts in the Earth's rotation, of course, but scientists have developed incredibly precise methods to measure them. They rely on atomic clocks, which are arguably the most accurate timekeepers ever conceived and made by humankind. Atomic clocks achieve their unparalleled accuracy by using the natural, consistent vibrations of atoms, such as cesium atoms, to meticulously keep time. These clocks are so incredibly precise that they would only lose or gain a single second over a staggering period of 300 million years. By carefully comparing atomic time, known as Coordinated Universal Time, UTC, with Earth's actual rotation, designated as UT1, scientists are able to spot and quantify these incredibly subtle millisecond differences in the Earth's spin. These seemingly insignificant shifts, measured in milliseconds, actually matter a great deal for both scientific research and modern technology. They play a crucial role in helping us navigate the globe accurately, maintain reliable communication networks, and keep our interconnected world in precise synchronization. Even the smallest tick, the briefest moment, can ultimately have surprisingly big consequences in the grand scheme of things. Shorter days aren't new. Earth has been breaking records recently. For centuries, days were getting longer, but in the last few years, Earth's spin has sped up. In 2020, Earth broke the shortest day record 28 times, shattering the old mark from 2005. On June 29, 2022, Earth set the current record, 1.59 milliseconds shorter than 24 hours. Another day, in July 2022, came close, and now, July 22, 2025, could break the record again. These aren't random flukes. They're part of a bigger story about our planet's changing systems. The big question, why now? This speed-up goes against the long-term trend. It's like a ball rolling faster on its own. Scientists want to know what's pushing it. Each record is a clue to the forces at work inside and around our planet. The mystery is far from solved. What's making Earth spin faster? The moon's gravity has always been a major influence, creating tides and acting like a brake on Earth's rotation. For billions of years, this tidal friction has slowed Earth down. Days used to be shorter in the age of dinosaurs. The moon's braking effect should make days longer, not shorter. So something else must be overpowering the moon's influence right now. It's like having your foot on the brake, but someone else is pressing the accelerator. The moon sets the baseline, but other forces are now in play. These new factors are more variable and harder to predict. They involve everything from the air above us to the molten metal deep inside Earth. The moon's role is constant, but the real action is happening elsewhere. Let's look at what else could be speeding us up. If the moon is slowing us down, what's speeding us up? Scientists point to melting glaciers, shifting air, and the churning core. Melting ice moves mass from the poles toward the equator, like a skater pulling in her arms to spin faster. This post-glacial rebound effect is accelerating as climate change melts more ice. The atmosphere also plays a role. Winds and pressure changes can nudge Earth's spin by tiny amounts. Large weather patterns like El Niño might be contributing to the current speed-up. Deep inside, the liquid outer core's movement can either drag or speed up the surface. Changes in the core's flow are a big wild card for Earth's rotation. All these forces interact in complex ways. The result? Earth's spin is more dynamic than we ever imagined. Scientists are still piecing together how these factors combine. If we can't feel these changes, why do they matter? Because our technology depends on precise timing. GPS, for example, relies on atomic clocks and accurate models of Earth's rotation. Even a few milliseconds error can throw off navigation, especially for airplanes or scientific research. Financial markets and the internet also depend on synchronized clocks. When Earth's spin changes, engineers must update systems to keep everything running smoothly. Tracking these short days is critical for our high-tech world. Tiny shifts can have big impacts on navigation, communication, and security. That's why scientists watch Earth's every move. To keep clocks in sync with Earth's rotation, scientists invented the leap second in 1972. When Earth slows down, we add a second to UTC, 27 times so far. But now, with Earth speeding up, we might need a negative leap second, removing a second from our clocks. This has never been done before and could cause problems for computer systems. The debate is on. Some say leap seconds keep us connected to Earth's reality. Others argue they disrupt technology. A decision has been made to stop adding leap seconds by 2035. Until then, the possibility of a negative leap second shows how unusual this period is. It's a new challenge for scientists and engineers. The leap second debate highlights the tension between nature and technology. Our timekeeping is entering uncharted territory. Tracking Earth's rotation is like taking its pulse. It reveals the health and dynamics of our planet. These millisecond changes help us understand climate change, geophysical hazards, and the connections between Earth's systems. The more we know, the better we can predict and prepare for the future. Will days keep getting shorter, or will the moon's slow-down return? The answers will shape how we manage time and technology. Each tiny shift is a clue in a global detective story. As we experience possibly the shortest day ever, let's marvel at our ever-changing world.